Alright, this is Chapter 4 homework for Physics 102. A battery having an EMF of 9 volts delivers this current when connected with a 72 ohm load. Determine the internal resistance of the battery. So what we have here is a battery that has an ideal EMF of 9 volts. Right, but that battery actually also has an internal resistance. Right, so this is the actual battery. It has this source of electromotive force through some chemical reaction or whatever, as well as an internal resistance. And then it's connected to a 72 ohm load. So I have another resistance. And then through this I get a current of 117 milliamps. That's 0.117 amps. I want to know the internal resistance of the battery. I'm going to use the loop rule that says that the sum of the voltages across a loop is equal to 0. I'm just going to add up the voltages for each thing. So I'll start here and go in that direction. I have a plus 9 volts minus your current, which is 0.117 amps, times the resistance, minus your current, times 72 ohms. That's equal to 0. And then I'm going to solve this for R, and I get R equals 4.92 ohms. A 4 ohm, 8 ohm, and 12 ohm resistor are connected in series with a 24 volt battery. What is the equivalent resistance in the current? And then also repeat it for parallel. So for part A, let's just draw the circuit first. 24 volt, 4, 8, and 12 ohm resistors. They're hooked up like that in series with this battery. I first want to know the equivalent resistance. Remember, for resistors in series, we have a couple of rules. First is that the equivalent resistance is just the sum Alright, the resistors have the same current, and the sum of the voltages is equal to the total voltage. All right, let me rewrite that. That is that the voltage across resistor 1 plus the voltage across resistor 2 plus however many resistors you have is equal to the voltage across your power supply or the battery. And then of course we also have Ohm's law, which just says that VIR. Those are for resistors in series. Need to know those rules and be able to apply them. So here my equivalent resistance is just 4 plus 8 plus 12. That's equal to 24 ohms. So that's the first part. And then I want to know the current in each resistor. Well, whatever current I have coming through here is going to go through each resistor, because it has to. It has nowhere else to go. I can redraw this circuit just like this. And so this current is the same as this current. So that current is V over R equivalent. That's 24 over 24, which is 1 amp. All right, and that's equal to the current in resistor 1, resistance 2, and the third resistor. Same current in all three. All the resistors have the same current. All right, part B, or rather part C, I'm going to repeat. See, this was part A, this was part B, and now I'm going to repeat it for part C, but now all my resistors are going to be in parallel. The 4, an 8, and a 12 ohm resistor. First I want to know the equivalent resistance. For resistors in parallel, I have these rules. I have the equivalent of resistance is equal to 1 over the sum of the inverses. 1 over R1 is 1 over R2, dot, dot, dot. All right, that's the equivalent resistance for those in parallel. I also know that these resistors in parallel all have the same current. Excuse me, not the same current, all have the same voltage. All right, so the 4, the 8, and the 12 ohm resistors are all going to carry 24 volts. I also know that the current, the sum of the currents in all the resistors, I1 plus I2 plus I3, however many resistors there are in parallel, that's equal to the total incoming current. All right, so for example, if I have 2 amps coming in here, I have 2 identical resistors here. Let's say I'll have 1 amp there, so I have to have 1 amp there. It splits it up. Not necessarily evenly, like I could have 0.5 amps here and 1.5 amps here. But the sum of those 2 currents has to add up to equal the total incoming current. All right, so I want to know what is the current through all of the resistors. However, I know that the voltage across each resistor is 24 volts, so it becomes pretty easy because I know the voltage across each resistor is 24. So I can just use Ohm's law. So for I1 is going to be 24 over 12. 24 volts over 12 ohms. That's equal to 2 amps. I2 is going to be 24 volts over 8 ohms. That's equal to 3 amps. And then I3 is 24 volts over 4 ohms. That's equal to 6 amps. All right, so those are the currents. I also need to know the equivalent resistance. It asks for that. The equivalent resistance is equal to 1 over 12 plus 1 over 8 plus 1 over 4. Let's see, that's 2 plus 3 is 5. 11 24ths. It's 2.2 ohms. All right, so that's my equivalent resistance, and these are my currents. I can check my answer for those currents based on this rule. The sum of those currents, that is 6 plus 3 plus 2, which is equal to 11, should equal the total current. So if I rewrite this circuit with just my equivalent resistance, I have 24 volts, 2.2 ohms. This current should equal the sum of those currents. And that current is equal to 24 over 2.2. And 24 over 2.2 is equal to 11. And notice that that also equals 6 plus 3 plus 2. So that's just a little check to verify my answer is correct. 9 and a 6 ohm resistor are connected in series with a power supply. Voltage drop across 6 ohm resistor is 12 volts. Find the voltage output of the power supply. Let's draw the circuit. They're in series. My power supply. I have a 9 ohm and a 6 ohm. And I don't know the voltage across this power supply, but I want to know it. However, I know that the voltage drop across this resistor is 12 volts, right there. The easiest way to do this would be to find the current through this resistor right here. That current, I, is equal to V over R. That's 12 over 6. Is equal to 2 amps. If I have 2 amps going through that resistor, remember for resistors in series, they have the same current. And I also have 2 amps going through this resistor. Right? So if I have 2 amps going through this resistor, that means that my voltage through this, V is equal I times R, is 18 volts. And then, if I have 18 volts here and 12 volts here, I have 18 plus 12, which is equal to 30 volts, and that's my answer. Now, another way that you could do this is that you could say that the equivalent resistance is equal to 9 plus 6 is equal to 15 ohms. I know that I have 2 amps going through that equivalent resistor, so V is equal to I times R equivalent, which is 2 times 15, which is 30 volts. 2 amps, which is our current going through the 6 ohm resistor, times 15 ohms, which is my equivalent resistance, that's 30 volts. So there are often multiple ways to get to the answer, but it's 30 volts the answer. The same 2 resistors are connected in parallel across the power supply, and the current through the 9 ohm resistor is 0.25 amps. So let's draw a circuit here. I have a 9 and a 12 volt, or 9 and a 6 ohm resistor. I want to know what this voltage is, and it says that the current is 0.25 amps through the 9 ohm resistor. So this current is equal to 0.25 amps. I know that the voltage across this resistor and the voltage across this resistor are the same, and they're going to be the same as the voltage across the power supply. So I can just say that the voltage across the 9 ohm resistor is equal to the voltage across the battery, and that's the voltage across the 9 ohm resistor is I times R. That's 0.25 amps times 9 ohms. That's equal to 9/4 volts. R was at 2 1/4 volts, 2.25 volts. All right, so I have 2.25 volts here. I also have 2.25 volts here, and I have 2.25 volts here. Resistors in parallel have the same voltage. All right, find the equivalent resistance of this, and then find the current resistor in each. All right, so what you want to do here is take the smallest parallel or series component and find the equivalent. So here I have these two, which are obviously in series. The equivalent of those is 1 plus 1 equals 2 ohms. Then I also have these two, which are in parallel, only in parallel. There's no series components embedded. And so the equivalent of that is 1 over 2 plus 1 over 2, which is equal to 1 ohm. I can redraw my circuit now. A 12 volt battery. This is now 2 ohms. That's this resistance. And now this is going to be, let's see, I actually left it out. I'm going to draw in another resistor here. This is my 1 ohm resistor. That's from here. And then I have another 1 ohm resistor. It's 12 volts. I can draw one more circuit. I'm going to combine those two 1 ohm resistors. You might not need to draw all these steps, but I'm going to do it here just for practice. I have a 2 ohm and a 2 ohm. These are just in parallel. And so if I find the equivalent resistance, 1 over 2 plus 1 over 2. I've already done that. That's 1 ohm. So that's my equivalent resistance. That was part of the answer. The equivalent resistance is 1 ohm. And now I also want to find the voltage and current through each of the resistors. And this is going to be similar to what we did with capacitor circuits, where we sort of work backwards. I'm going to make a little table here. This will be my resistor number, and then I have my voltage, and then my current. And you know, if we get any one of these, then we can fill in the other one by Ohm's law. So if I get the voltage, then I know that I is just V over R. 1, 2, 3, 4, 5. If I get the current, then I know that V is just I times R. Alright, so first, I'm going to start working back here. I want to know this current. That current is equal to V over R, 12 over 1, or 12 amps. Alright, then I'm going to step back, and I'm going to look at this circuit right here. I know that I have two resistors in parallel. A couple things that I can say. First of all, I know that I have 12 amps going here. And so since these two resistors are identical, I know that I have 6 amps going through each of these. That's only because those two resistors are identical. I can also say, and you can see this from Ohm's law, because V equals IR, so the voltage across each of these is 12 volts. That is 6 times 2 is 12. So the voltage across each of these is 12 volts. You could also say that just from the fact that resistors in parallel have the same voltage. And these are two resistors hooked up to a 12 volt battery, so they have 12 volts of potential. All right, now let's go back up to here. I have 6 amps going through here, 6 amps going through here, 12 volts here. I have these two 1 ohm resistors. They're going to split up that 12 volts, so each of them is going to get 6 volts. Right, each of those resistors is going to get 6 volts. And you can also see that from Ohm's law. I is equal to V times R, or excuse me, V is equal to I times R. I is 6 amps times your resistance, which is 1 ohm. That gives you a 6 volts. Let's go ahead and put in some numbers here. Let's see, this was R5. So I have R5 as 6 volts and 6 amps. I also know that the current through R1 and R2 is 6 amps. I have 6 amps here. That's this number. All right. So I can put in I1 and I2. It's 6 amps and 6 amps. And then from Ohm's law, I can find that that V is equal to I times R for R1 and R2. Each of them is 1 ohm. Each of them has 6 amps. So I'm going to have 6 volts for both of these. Notice that I could also see this because I have 12 volts here and I have 2 identical resistors. So they're going to split the voltage evenly. They're each going to get 6 volts because they're identical. All right, now we're just left with resistors 3 and 4. This was the equivalent of resistors 3 and 4 right here. And I know that as 6 volts. Now, because resistors in parallel have the same potential, I know that both of these resistors is going to have 6 volts. Because the equivalent resistor had 6 volts. So I'm going to go ahead and write that in. 6 volts and 6 volts. And then I can find the current with 2 ohms. I know that each of them is going to have 3 amps. Notice that I could have also seen that because I know that there is a, erase some of this. I know that there is a total current of 6 amps coming into this circuit. They're going into 2 identical resistors in a parallel branch. So they're going to split that current evenly. And so I'm going to have 3 amps and 3 amps. And then that's going to come back together over here to give me another 6 amps. All right, find the equivalent resistance of this circuit in this figure. So like I did before, and here I'm not going to draw all the circuits because this is a little easier and I don't have to find all the currents and voltages. If I combine these two, that's going to be 1 over 10 plus 1 over 5. See, that's 1/10 plus 2/10 is 3/10. That's 10/3. 1 over 3/10, which is 10/3, which is 3 1/3 or 3.33. And then, so I can replace this with 3.33. And then I can combine these two. 4 plus 3.33, 7.33 ohms. 7.33 ohms. All right. I'm going to redraw it now. I have 3 ohms, 7.33, and then another 3 ohms. Find the equivalent of these two. That is 1 over 7.33 plus 1 over 3. And that gives me 2.1 ohms. And then I've combined that 2.1 ohms because I replaced these two with a 2.1. I can add that to 3. So my total equivalent resistance is going to be 3 plus 2.1, or 5.1 ohms. 5.1 ohms, that's my equivalent resistance. And then I also want to know if the total power supplied to the circuit is 4 watts, find the EMF of the battery. What is the voltage of the battery? Well, I know the resistance now. The resistance is 5.1 ohms. I know that the power is equal to V squared over R. So I can solve for V. Which gives me the square root of 4 times 5.1 is 4.5 volts. Alright, I have a couple of changes that I've made on this problem. First of all, the ammeter shown in this figure reads 1.789. That's different from what you have in your book. Sorry that I didn't get that change in. I also want to make some other changes here. V2 is going to be 20 volts. And instead of being the ammeter right here, just ignore that, your ammeter is going to be right here. So that means that I2 is going to equal 1.789 amps. And it's traveling downward through there, through that branch of the circuit, through the 4 ohm resistor and across the 20 volt battery. Now, I want to know what is I1 and I3. I already know what V2 is, that's given. Okay, so I'm going to write my equations for the left and right loops. Left first. I'm going to start here and travel in that direction. So I'm going to have first 10 volts minus 3I1. It's minus 3I1 because I'm going with the current across the 3 ohm resistor. Minus 20. Now I'm coming around here and coming up there. It's minus 20 because I'm going from low to high. So I see a negative change in potential. Plus 4I2. It's plus because I'm going against the current. Notice here that I2 is going down. All right, so I'm going against that current. And so it's plus 4I2. That's equal to 0. That's the loop rule. I can also do the right loop. I'm going to start right here and go in that direction. I get negative 12 because I'm going from high to low potential. Plus 1I3. So just plus I3. It's positive because I'm going against the current. I'm going in this direction, but the current is going in that direction. So I'm traveling against the current. Minus 4I2. I'm going with the current across that 4 ohm resistor, and plus 20. So I'm going from low to high potential. That's equal to 0. I want to know I1 and I3. I know I2, so this is fairly simple to get I1 and I3. To get I1, I solve the left equation. Let's see, that's going to be 10 minus 20 plus 4I2. divided by positive 3. I'm putting in my value for I2, 1.789. I get this as negative 0.948 amps. All right, so I know then that I1, which I said was going down, is actually 0.948 amps up on that branch of the circuit. So I1 is actually traveling in this direction. And then if I want to know I3 is equal to 12 plus 4I2 minus 20. Taking the value that I have for I2, I get I3 is negative 0.844. All right, that means that I3 is 0.844 amps. I chose it to be, let's see, what was the direction up here? It was listed as downward, so I know that it is upwards, 0.844 amps up. So I know that I3, instead of going down, is actually traveling in that direction. Now, I can check all this by taking my junction rule. The junction rule says that the current coming into any junction is equal to the current going out of a junction. Let's pick this junction. I have I1 coming in, I2 coming in, and I3 all coming into that junction. And so my junction rule says I1 plus I2 plus I3 equals 0. So I can try this. I get negative 0.948 minus 0.844 plus 1.789. That should equal 0. And it is basically, it's 0.003, but it's equal to 0. All right, so that's a check. Sometimes when you round off, it doesn't come out exactly right, but it's within sig figs is equal to 0. Determine the current in each branch of the circuit shown in this figure. Likely it has something like this on the test. The previous one was a little bit easier. This one's a little more difficult. First thing you want to do on one of these is just select directions for the current. Assign and select directions for the current. I'm going to say that I1 is in this direction. It travels from this point through that left loop down to this point. I2, I'll choose to be going down. So I2 travels from here down to here. And then I3, I will take to be traveling, what's this, clockwise. I'll take this to be I3. All right, and then I want to write 3 equations because I have 3 unknowns. I want to know each of these currents, I1, I2, and I3. I like to choose the left side, the right side, and then the junction rule. But notice that there are some other, there's also the outer loop that you can also choose. All right, so first I'll take my first equation will be the left side. I'm going to start right here and go through the circuit in this direction. So that's going to give me plus 10 minus 1I1 minus 12 plus 2I2. That's equal to 0. That's the loop rule, which says that the sum of the voltages equals 0. Then I'll take the right loop. I'm going to start right here and go in this direction. The first thing I encounter is that 5 ohm resistor. I'm going against, actually no, excuse me, I'm sorry. I'm going to start up here and go in this direction. First thing I encounter is that 5 ohm resistor, and I'm going with the current. So I have minus 5 I3 because I'm going across this resistor with the current. And remember, this direction that I chose for the current is just something that I chose. It doesn't have any physical meaning at all. It's just something that you choose. It doesn't matter what you choose. All right, so minus 5 I3. Then I get minus 12 and plus 2I2, because I'm going against the direction that I chose. And that's equal to 0. And then the junction rule is nice. It's fairly simple. Just pick a junction, any junction, where 3 or more lines are coming together. Here I say my incoming current is equal to my outgoing current. So here I have no incoming currents, I just have outgoing currents. So it says then that I1 plus I2 plus I3 equals 0. It only equals 0 because there is no incoming current. All right, so one side is 0, but it could be I1 equals I2 plus I3, and we worked through some examples like that in class. All right, so we're going to do this by substitution. As we did in class, you can do this by simplifying the matrix, but I'm not going to do that here. First, let me label these equations. I'll call this equation 1, equation 2, and equation 3. I'm going to solve equation 1 for I1. You get I1 equals 2I2 minus 2. Then I'm going to solve equation 2 for I3. And I get I3 equals 2I2 minus 12 over 5. All right, so I've solved both of those for I1, which is now in terms of I2, and I3, which is now in terms of I2. Now I can sub both of these equations into equation 3. This is generally the MO for doing this. You solve your two loop equations for different variables in terms of the same variable. In this case, I solved for I1 in terms of I2 and I3 in terms of I2. And then sub it into the junction equation, and then you'll have just one unknown. All right, so I have I1 plus I2 plus I3 equals 0. So I have I1 is 2I2 minus 2 plus I2 plus I3, which is 2I2 minus 12 over 5. And that's all equal to 0. Now, if I solve this, I find that I2 equals 1.3 amps. It comes out positive, so I know that I chose the direction correctly, so it's 1.3 amps downward. So that's one part of my answer. And now that I know I2, finding I1 and I3 is fairly trivial because I already have these equations. So I know that I1 equals 2 times 1.3 minus 2, so it's 0.6 amps. And I chose the direction for I1 to be down, and so I1 is also going to be down because it came out positive. In a similar way, I3, plugging in I2 there, I get I3 to be negative 1.9 amps. Now, I chose I3 to be down, so I know that I3 is actually going to be 1.9 amps up. So that's I3. Because it came out negative, that means that I chose the direction incorrectly. All right, so now you switch the direction of that current. That's the answer. Very likely to have something like this. All right, consider a series R circuit for which C equals 6 microfarads, R is 2 times 10 to the 6 ohms, and our EMF is 20 volts. Find the time constant of the circuit, A. All right, the time constant, tau, is equal to the resistance times the capacitance. That's going to be 2 times 10 to the 6 ohms times the capacitance, which is 6 microfarads. That's 6 times 10 to the minus 6 farads. Notice that these two cancel out, and I'm just left with 2 times 6, which is 12 seconds. All right, that is a characteristic time for the charging and discharging of this capacitor, this RC circuit. Remember, it requires 10 time constants for us to consider that a capacitor is fully charged or discharged. So in this case, it would take 120 seconds to fully discharge or to fully charge the capacitor. Also want to know what is the maximum charge on the switch, or on the capacitor after the switch in the circuit is closed. So when you turn the circuit on, how long does it take, or what is the maximum charge that it's going to receive? The maximum charge is Q equals C times V. That is 6 microfarads times my voltage of 20 volts. That is 120 microcoulombs. So that's the maximum amount of charge that you will acquire in this capacitor. I have a series RC circuit, 1 mega ohm, 5 microfarads, and 30 volts. How long does it take for the capacitor to be fully charged? Just draw this, a 30 volt of a switch. It's initially open. Have a 1 mega ohm and a 5 microfarad capacitor. When I close this switch and engage the circuit, how long does it take for the capacitor to be fully charged? Well, my time constant is R times C. It's 1 mega ohm times 5 microfarads. The mega, which is 10 to the positive 6, and the micro, which is 10 to the minus 6, they cancel one another out. So this gives me 5 seconds. So it requires, how long does it take for the capacitor to be fully charged? Requires 10 tau to be fully charged, which is 50 seconds. All right, and now I also want to know what is the charge at t equal 10 seconds. Well, I know that it's not fully charged. All right, so I can calculate the charge as a function of time. This is Q max times 1 minus e to the minus t over RC. Right, that RC again is our time constant. It's this characteristic time in this exponential function. Q is equal to CV. So I can put in some values here. Let's see, C is 5 microfarads. V for this one was 30 volts. So when it's maximum charge, it's going to have 150 microcoulombs. 5 times 30 is 150. 1 minus e to the minus t, which is 10 seconds, over RC, which is 5 seconds. I get 130 microcoulombs. You want to make sure that you know how to do the exponential function in your calculator. Just make sure you know the mechanics of doing that. All right, one more. An electric heater is rated at 1300 watts, toaster at 1000 watts, and electric grill at 1500 watts. 3 appliances are connected in parallel to a common 120 volt circuit. How much current does each appliance draw? When I have them all in parallel, they all have the same voltage. So I can find the current for each of them. I of the heater is equal to P over V. That's going to be 1300 watts over 120 volts. That's going to be 11 amps. It draws 11 amps of current. I for the toaster equals 1000 watts over 120 volts. That's equal to 8.3 amps. And I for the grill, the current for the grill is 1500 watts over 120 volts. Everything in your house, well, most of your appliances operate at 120 volts unless they're on a separate circuit. Like your dryer and your electric stove and your electric hot water heater. Those operate at higher voltages. Okay, let's see, 15 over 120, that's 13 amps. All right, so each of these draws this current. Now, since they're all in parallel, each of these draws that current that we just calculated, and so the total current is going to be the sum of all of those. So that total current is going to be 11 plus 8.3 plus 13. That's equal to 32 amps. That's the total current. That is part A. For part B, since I have 32 amps, but I only have a 30 amp breaker, then that circuit breaker is going to kick off. So the answer to part B is no, because you exceed the max current. So whenever they lay out the circuit for your house, you have to make sure that you have enough circuits so that you don't exceed the maximum current for each of the particular breakers, so that you don't have, 4 heaters, for example, all on one circuit.